Hey everyone, this video is going to be about the substantial derivative or the total derivative. And so to get started, we'll be looking at it from the viewpoint of an infinitesimal fluid element moving through space, which you can see I described it in a little bit of detail in my flow models video. And so because it is moving through space, the fluid element has a certain velocity, and I'm going to be doing this in Cartesian coordinates because it's the easiest. So it's moving through Cartesian space with a velocity u I hat plus v j hat plus w k hat. So u, v, and w are the x, y, z components of the velocity, and then I hat, j hat, k hat are the unit vectors in each of those directions. So since it's moving through space, the velocity is going to be dependent on the x position, the y position, and the z position. So here at 1, the x position, y, and z are all going to be different than here at 2, where it's going to have different x, y, z. We're also talking about an unsteady flow, so we're going to have a time, it's going to be changing with time as well. So we have the u as a function of the x position, y position, z position, and time, and the same goes for the v and the w components of velocity as well. So I'm going to be doing this kind of derivation with an arbitrary flow variable, and we're just going to use density here. So density again is also going to vary with the x, y, z position and time. So just in general, we have points 1 and 2 here. It's moving it's moving from point 1 to 2. And so at point 1, we have the density at 1 is a function of the position at 1, which is xy, x1, y1, z1, and then the time at 1, which is t1. And then the density at 2 is the density at position x2, y2, z2 at time t2. I forgot. Okay. And the same goes for the u, v, and w velocities as well. So u1 will be u of x1, y1, z1, t1, and so forth. Okay, so what we can do is we can take a Taylor series expansion of the density about point 1. So in my other video I did a Taylor series video, and it was for a single variable. Now we're doing it for a multivariable. So if we're doing a single variable where rho is just a function of x, you'd have this rho2 is equal to rho1 plus d rho dx, and this would be a d instead of a del, or I call it a del because it's a partial derivative here. And it'll be x2 minus x1, and then you'd have, instead of that, you'd have like the next higher order term with the derivative with respect to x. But here we have to do it the first order term for each of the variables that we have, and then we have a higher order term. So we have the rho2 is equal to rho1 plus the partial derivative of density with respect to x at point 1 times the change from 2 to 1 in the x direction, and then we have for the y, and then for the z, and then for the time. And then we have the higher order terms, so we're going to ignore those for now. Okay, so then what we do is we subtract rho1 from both sides, and then we divide both sides by t2 minus t1. So we end up with rho2 minus rho1 over t2 minus t1, and then we divide it by t2 minus t1 here, here, and here. So we have this d rho dx times this change in x over change in t, and then d rho dy times the change in y over change in t, and then the same for the z direction. Okay, and then we also have, that I forgot to put here, we still have the d rho dt term at 1. Looks like I forgot a lot of things. And this is also at 1. Okay. So what this here is, and what these are as well, it's the average change. So it's the average change of the density with respect to time, and then here's the average change in the x position, the average change in the y, and the z positions with respect to time. So what we can do is we can take a limit as time t2 goes to the time t1. So what we're doing physically is kind of moving this element kind of closer and closer back to where we were at point 1, so infinitely close to where we were. So when we take the limit as time 2 approaches time 1 of rho2 minus rho1 over t2 minus t1, we get this capital D rho over capital dt, and that's the substantial derivative or total derivative, depending on how you say it, which is physically different from the from if I write, if I just write this partial derivative d rho dt. So the substantial derivative is saying that we're looking at this fluid element as it's moving, and as it goes through point 1, so it's coming from here, and then as it goes through point 1, how is its density changing? As opposed to the d rho dt, this lowercase, or the partial derivative d rho dt, that's saying I'm looking at point 1, how is the density of point 1 changing with time? So for the substantial derivative, we're looking at a fluid element moving and saying how does it change at this point 1. And then for the lowercase, or partial derivative d rho dt, we're looking at only point 1 and saying how's the density at that point changing. And this is really important as you start deriving the conservation equations. Okay, so in the same way that we took the limit here, we could take the limit for each of these terms here, which I did up here, and you end up getting just the velocity u, v, and w. Now I'm going to erase this to go into the next part. Okay, and this also. Okay, so from what we just had, if you can always scroll back in the video if you don't remember what it was, but we can write now the equation substituting in all these limits, and we have this substantial derivative is equal to, we have the u velocity times the partial derivative of the density with respect to x plus the v velocity. I'm going to just erase all this as well. Plus the v velocity partial derivative with respect to y plus the w velocity partial derivative with respect to z plus the partial derivative of the density with respect to time. Okay, so what we can see here is I'm going to take out the rho density because that can be any flow field parameter. So what I'm going to do is I'm just going to write a general version of the equation of the substantial derivative, and I'm going to use these open parentheses to describe any flow field parameter. That's what you would plug in for rho, or it could be pressure, or it could be temperature. So we have this d dt is equal to u d dx plus v d dy plus w d dz plus d dt. Okay, sorry for all the erasing, I just always run out of room. Okay, so that's the general form of the substantial derivative. But we want to make it a more general case because right now this is only for Cartesian coordinates because we have the x, y, z, so we want to make it useful for cylindrical or spherical coordinates as well. So what we can do is take a look at this term. This is called the del operator in vector calculus. And that's actually equivalent to the d dx in the I direction plus d dy in the j direction plus d dz in the k direction. Again, this is for Cartesian, but it'll generalize once we finish it. Okay, and then if we look at the velocity vector, like we said before, was u I hat plus v j hat plus w k hat. So what you can do is you can see that this term right here is actually going to be v dot this operator here, and I can put in these generalized parentheses here as well. So it can be any flow field parameter. So if we look at that, it would be v dot del, and that would be ui plus vj plus wk. That's our v dot product with d dx I plus d dy k plus d dz, oops, that's a j, k. And then when you take the dot product, these two, these two, these two. So you end up having v dot del is going to be equal to u ddx plus v ddy plus w ddz, like that, which is this term here. And then we have this partial derivative of the flow field parameter with respect to time. So what we can do is we can just write it down then as the final version is the substantial derivative here is going to be equal to this time derivative, like this, plus this term here, which is the velocity dotted with this gradient, essentially. So this is your full total derivative or substantial derivative. So this is called the local derivative. This is called the convective derivative. Convective because there's some velocity here. So one of the examples that I like that makes a lot of sense to me is from Anderson's book. Any of his books, really, because he goes over it multiple times. Is imagine you're kind of like on a mountain and you're walking into a cave and it's cooler inside the cave. So you're it's warm outside the cave, it's cool inside the cave. So you're walking into the cave, and as you walk into the cave, you'll feel a change in temperature as it cools you down while you're walking in. And that's the convective derivative here. And then imagine that as you're walking into this cave, somebody throws a snowball at you and it hits you, and then right at that instant you feel colder because you got hit by a snowball, and that's this instantaneous local derivative. So the convective derivative is you walking into a cave, but you feel this, or the total derivative, right, is you walk into a cave, you're getting cooler as you move in from the convective derivative, and then somebody throws a snowball or somehow something makes you feel colder at that instant, and that's this local derivative. So that's the best way that makes sense to me in terms of describing what the total derivative or substantial derivative actually is. And that'll help us moving forward with the deriving and governing equations. So thank you for watching.